All right, hello everyone. Welcome to my channel. This is a channel for educational purposes, and we look at theories of everything that have inspired me from the past, and we go deep into them and see how they can be used to help you out with your paradigm shifting, your awakening to 5D consciousness, and your formation of a holistic worldview. Today is our 517th video on the reciprocal system of theory from Dewey B. Larson. And in 1959, Mr. Larson articulated his two fundamental postulates about how he believed the universe operated. The first postulate is the primary one, where he says that the universe is composed entirely of motion, not matter, not energy, but motion. And that the universe is composed entirely of motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, so the universe is made out of motion. Motion is the relationship between space and time. And in particular, he's talking about a kind of motion that he calls scalar motion. Scalar motion is a motion that has a magnitude but has no specific direction. You can envision a scalar motion using a balloon that you put dots on. If you blow up the balloon, all the dots are moving away from each other. But they're not moving in any specific direction. Every dot will be moving away from every other dot. And that is the fundamental motion that is the source of all manifestation. Larson calls that the progression. And then that is really anti-gravity motion. Then the reverse of that motion is what he calls gravity. The inward motion of that balloon, surface of that balloon, would be the gravity. And so then he goes from there, takes a second postulate, which is that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute and its geometry is Euclidean. And he plugs the postulates into those rules and arrives at a theoretical universe, how the universe operates, what the universe looks like if it operates the way that he says it does. And then he compares his theoretical universe with the measured empirical universe of the modern scientists. And he does that in books like the one we have in front of us today, Basic Properties of Matter, which is primarily on chemistry. And Larson arrives at equations for many of the basic properties of matter and then compares what he's got with the scientific tables. And we are in chapter 25 of this book, getting close to the end. Chapter 25 is on radioactivity. And I think we're just going to get right into it. We may or may not get to all the way to the end of this chapter here today. Okay. Radioactivity, taken from the middle of the chapter to start. If you want to get a deeper sense of the reciprocal system, you want to watch one of my first 474 videos on this subject, where I go into the postulates a little bit deeper and explain the ramifications and so on, the discrete unit postulate and the 3 dimensions and the space and time reciprocity. But for today, I'm just going to assume that you have working knowledge. Okay. In those regions where the magnetic ionization level is 0 or near 0, all of the 117 possible elements are stable, and there is no alpha radioactivity. The heavy element content of young matter is low because atom building is a cumulative process, and this young matter has not had time to produce more than a relatively small number of the more complex atoms. but probability considerations make it inevitable that some atoms of the higher groups will be formed in the younger aggregates, particularly where older matter is dispersed into space by explosive processes. Older matter dispersed into space by explosive processes has been accreted by these younger structures. Thus, although aggregates composed primarily of young matter have a much lower heavy element content than those composed of older matter, they do contain an appreciable number of the very heavy elements, including the trans-uranium elements that are absent from terrestrial matter. The significance of this point will be explained in Volume 3. If matter from a region of zero magnetic ionization is transferred to a region such as the surface of the Earth, where the ionization level is unity or above, the stability limit in terms of atomic number drops and radioactivity is initiated. Whether the material constituents of the Earth acquired the unit magnetic ionization level at the time that the Earth assumed its present status as a planet, or reached this level at some earlier or later date, is not definitely indicated by the information now available. There is some evidence suggesting that this change took place in a considerably earlier era. But in any event, the situation with respect to the activity of the elements now undergoing alpha radioactivity is essentially the same. They originated in a region of zero or near zero magnetic ionization and either remained in that region while the magnetic ionization level increased, or in some manner, the nature of which is immaterial in the present connection, were transferred to their present locations where they have become radioactive for the reason stated. As noted above, another source of natural radioactivity is atomic rearrangement resulting from interaction of material atoms with high energy particles, principally the cosmic rays and their derivatives. In such reactions, stable isotopes of one kind or another are converted into unstable isotopes, and the latter then become sources of radioactivity, mostly of the beta type. The level of beta radioactivity produced in this manner is quite low. The very intense activity of the same general nature that is indicated by the radio and X-ray emission from certain kinds of astronomical objects originates by means of a different process, examination of which will be deferred until the nature and behavior of the objects from which the emissions are observed are developed in Volume 3. The processes that constitute natural radioactivity can be duplicated experimentally, together with a great variety of similar atomic transformations, which presumably also occur naturally under appropriate circumstances, but have been observed only under experimental conditions. We may therefore combine our consideration of natural beta radioactivity, the so-called artificial radioactivity, and the other experimentally induced transformations into an examination of atomic transformations in general. Essentially, these transformations, regardless of the number and type of atoms or particles involved, are no different from the simple addition and decay reactions previously discussed. The most convenient way of describing these more complex events is to treat them as successive processes in which the reacting particles first join in an addition reaction and subsequently eject one or more particles from the combination. According to some of the theories currently in vogue, this is the way in which transformations actually take place. But for present purposes, it is immaterial whether or not the symbolic representation conforms to physical reality, and we will leave this question in abeyance. The formation of the isotope P30, phosphorus 30, from aluminum, the first artificial radioactive reaction discovered, may be represented as Al27 plus He4 yields phosphorus 30 plus N1. In this case, the two phases of the reaction are independent. in the sense that any combination which adds up to 30-1 can produce P30 plus N1, while there are many ways in which the 31-1 resultant of the combination Al27 plus He4 can be broken down. The final product may, for instance, be Si30 plus H1. The usual method of conducting transformation experiments is to accelerate a small atomic or subatomic unit to a very high velocity and cause it to impinge on a target. In general, the degree of fragmentation of the target atoms depends on the relative stability of those atoms and the kinetic energy of the incident particles. For example, if we use hydrogen atoms against an aluminum target at a relatively low energy level, we get results similar to those produced in the aluminum 27 plus helium 4 reaction previously discussed. Typical equations are Al27 plus H1 yields magnesium 24 plus He4, or aluminum 27 plus H1 yields silicon 27 plus N1. Greater energies cause further fragmentation and result in such rearrangements as Al27 plus H1 yields sodium 24 plus 3H1 plus N1 plus N1. The general principle that the degree of fragmentation is a function of the energy of the incident particles has an important bearing on the relative probabilities of various reactions at very high temperatures, and we'll have further consideration later. In the extreme situation where the target atom is heavy and inherently unstable, the fragments may be relatively large. In this case, the process is known as fission. The difference between the fission process and the transformation reactions previously described is merely a matter of degree, and the same relationships apply. Although it is possible in some instances to transform one stable isotope into another by an appropriate process, the more general rule is that if the original reactants are stable, the major product is unstable and therefore radioactive. The reason is, of course, that the stable isotopes have vibrational to rotational mass ratios within the stability zone, and any change in the ratio tends to move it out of that zone. As an example, the P30 isotope formed in the reaction between aluminum and helium atoms is below the stability zone. That is, it is deficient in vibrational mass. It therefore decays by the beta plus process to form a stable silicon isotope. P30 yields Si30. That's 30-0 yields 28-2. In the radioactive reactions of the heavy elements, the products often have substantial excesses of vibrational mass, and in these cases, successive beta emissions take place, resulting in decay chains in which the unstable isotopes move step by step towards stability. One of the relatively long chains of this type has been identified as the following: xenon 140, then going to cesium 140, barium 140, lanthanum 140, and then cesium 140. Before that, we had caesium 140. So I think that's what it's called. That's like 108-32 to 110-30 to 112-28 to 114-26 to 116 or 28. Sorry. Yeah. Okay. Eventually getting to 116-24. which is still below the stability zone. The figures in parentheses refer to the number of units of vibrational mass corresponding to the center of the zone of stability, and that was 22 for the last one, 116-24, as calculated for each element from equation 24-1. The original product, xenon 140, has 13 excess vibrational units and is thus far outside the stability zone. Successive beta emissions convert 2-unit quantities of vibrational mass to rotational mass, while the stable amount of vibrational mass gradually increases as the atomic number rises. On reaching CE140, the excess has been reduced to 2 units. This is within the stability margin, and the radioactivity therefore ceases. The foregoing description of the atomic transformation processes has been confined to the essential element of the transformation, the redistribution of the primary mass, and the collateral effects have either been ignored or left for later treatment. In the latter category are the mass-energy relations, which will be discussed in Chapter 27. The electric charges carried by some of the reacting substances or the reaction products have no significance in the present connection, as they only affect the energy relations. On first consideration, it might appear that the addition processes discussed in the preceding pages would provide the answer to the problem of accounting for the existence of the heavier members of the series of chemical elements. In current practice, this is taken for granted, and the question to be answered is accepted as being merely the issue as to what specific one or more of these processes is operative. The currently accepted hypothesis is that the raw material from which the elements are formed is hydrogen, and that mass is added to hydrogen by means of the addition processes. It is recognized that, with certain exceptions that will be considered later, the addition mechanisms are high-energy processes. Atoms approaching each other at low or moderate speeds normally rebound and take up positions at equilibrium distances. The additions take place only where speeds are high enough to overcome the resistance, and these speeds generally involve disruption of the structure of the target atoms, followed by some recombination. The only place now known in our galaxy where the energy concentration is at the level required for operation of these processes on a major scale is in the interiors of the stars. The accepted hypothesis, therefore, is that the atom building takes place in the stellar interiors, and that the products are subsequently scattered into the environment by supernova explosions. It has been demonstrated by laboratory experiments, and more dramatically in the explosion of the hydrogen bomb, that the mass 2 and mass 3 isotopes of hydrogen can be stimulated to combine into the mass 4 isotope of helium, with the release of large quantities of energy. This hydrogen conversion process is currently the most powerful source of energy known to science, aside from some highly speculative ideas that involve carrying gravitational attraction to hypothetical extremes. The attitude of the professional physicist has always been that the most energetic processes known to them must necessarily be the process by which energy is generated in the stars, even though they have had to revise their concept of the nature of this process twice already, the last time under very embarrassing circumstances. The current belief of both the physicists and the astronomers, therefore, is that the hydrogen conversion process is unquestionably the primary stellar energy source. It is further assumed that there are other addition processes operating in the stars by which atom building beyond the helium level is accomplished. It will be shown in Volume 3 that there is a mass of astronomical evidence demonstrating conclusively that this hydrogen conversion process cannot be the means by which the stellar energy is generated. But even without this evidence that demolishes the currently accepted assumption, any critical examination of the fundamentals of atom building will make it clear that high energy processes, inherently destructive, are not the answer to the problem. It is true that the formation of helium from isotopes of hydrogen proceeds in the right direction, but the fact is that the increase in atomic mass that results from the hydrogen conversion reaction is an incidental effect of a process that operates toward a different end. The primary objective of that process, the objective that supplies the probability difference that powers the process, is the conversion of unstable isotopes into stable isotopes. The fuel for the known hydrogen conversion process, that of the hydrogen bomb, and the experiments aimed at developing fusion power, is a mixture of these unstable hydrogen isotopes. The operating principle is merely a matter of speeding up the conversion, causing the reactants to do rapidly what they will do slowly of their own accord, if not subjected to stimulation. It is freely asserted that this is the same process as that by which energy is generated in the stars, and that the fusion experiments are designed to duplicate the stellar conditions. But the hydrogen in the stars is mainly in the form of stable mass 1 isotope, and there is no justification for assuming that this stable atomic structure can be induced to undergo the kind of a reaction to which the unstable isotopes are subject by reason of their instability. The mere fact that the conversion process would be exothermic if it occurred does not necessarily mean that it will take place spontaneously. The controlling factor is the relative probability, not the energy balance, and so far as we know, the mass 1 isotope of hydrogen is just as probable a structure as the helium atom under any physical conditions other than those to be discussed in chapter 26, the next chapter, that lead to atom building. At high temperatures, the chances of atomic breakup are improved, but this does not necessarily increase the proportion of helium in the final product. On the contrary, as noted earlier, a greater kinetic energy results in more fragmentation, and it therefore favors the smaller unit rather than the larger. A certain amount of recombination of the fragments produced under these high temperature conditions can be expected, particularly where the extreme conditions are only temporary, as in the explosion of the hydrogen bomb. But the relative amounts of the various possible products of recombination are determined by probability considerations. Inasmuch as stable isotopes are more probable than unstable isotopes, formation of the stable helium isotope from the atomic and subatomic fragments takes precedence over recombination of the unstable isotopes of hydrogen. But the mass 1 hydrogen isotope that is the principal constituent of the stars is just as stable as helium, and it has the advantage in a high energy environment of being the smaller unit, which makes it less susceptible to fragmentation and more capable of recombination if disrupted. Thus, it cannot be expected that recombination of fragments into helium under high energy conditions will occur on a large enough scale to constitute a major source of stellar energy. In this connection, it should be noted that the general tendency of high energy reactions in the material sector of the universe is to break down existing structures rather than build larger ones. The reason for this should be evident. The material sector is the low-speed sector, and the lower the speed of matter, the more pronounced its material character becomes. That is, the more it deviates from the speeds of the cosmic sector. It follows that, in general, the lower the speed, the greater the tendency to form combinations of the material type. Conversely, higher speeds lessen the material character of the matter and not only inhibit further combination, but tend to disrupt the combinations already existing. Furthermore, this increase in the amount of negative displacement is not, that's thermal or translational motion, is not conducive to building up positive displacement in the form of mass. Thus, the net result of the reactions in the high-speed environment of the stellar interiors can be expected to decrease rather than increase the average atomic weight of the matter participating in these reactions. An analogous process in a more familiar energy range is the pyrolysis of petroleum. Cracking of a paraffinic oil, for instance, yields products that, among other things, include substantial quantities of complex aromatic compounds. For example, one of those that makes its appearance is anthracene, a 24-atom molecule. There are few, if any, of the ring compounds, even the smaller ones, in the original material. Thus, it is evident that the high temperatures of this process have not only broken down the original hydrocarbon molecules into smaller molecules or atoms, but have also allowed some recombination into larger molecular units. Nevertheless, the general result of the cracking process is a drastic reduction in the average size of the molecules, the greater part of the mass being reduced to hydrogen, methane, and carbon. The point that needs to be recognized is that this is what high energy processes do to combinations such as atoms, regardless of whether those atoms are combinations of particles, as contended by conventional physics, or combinations of different forms of motion, as deduced from the postulates of the theory of the universe of motion. Such processes disrupt some or all of the original combinations. In the chaotic conditions generated by the application of powerful forces, there is a certain amount of recombination going on alongside the disintegration. This may result in the appearance of some new combination, some new isotopes, which may suggest that atom building is occurring. But in fact, these constructive events are merely incidental results of a destructive process. In the universe of motion, the raw material for atom building consists of massless particles, the decay products of cosmic rays. Conversion of these particles into simple atoms of matter and production of increasingly more massive atoms from the original units is a slow and gradual constructive process, not a high-energy destructive process. This assertion as to the general character of the atom-building process is confirmed by the astronomical evidence, which, as will be brought out in Volume 3, shows that atom building is taking place throughout the universe, not merely at special locations and under special conditions as envisioned in present-day theories. The details of the atom building processes in the universe of motion will be the subject of the next chapter. And so that is the end of this chapter 25 on radioactivity. And chapter 26 is called Atom Building. And then we just have chapter 27, which is on mass and energy. and that will be the end of this volume, volume 2. When he refers to volume 3 there, he's talking about his volume on astronomy called The Universe of Motion. And we will not be getting into that right away. Maybe in the future. It's a little bit more advanced of a study, at least once you get into after the first couple chapters. And there's like 31 chapters, and it's more advanced than this here, and this one's already pretty advanced. So after we get done with this book, we're going to go into Larson's theory of economics and read, maybe not read, but at least summarize his work called The Road to Permanent Prosperity. And then maybe get into some of Bruce Perret's work on his RS2 forum that he did before he passed away. And then we'll be moving on into different subjects: quantum arithmetic, synergetic geometry, music studies, music theory, music history, and some ancient history going back to the 1st century, and the Romans and the Jews and so on. Okay. Thank you for tuning in today. Stay tuned for tomorrow on Chapter 26, Atom Building, and have a great day.